Now, whenever we have the chain rule, if it was really obvious that it was the chain rule, doing the integration wasn't so bad. We did some of those examples yesterday. If I made it really obvious, you could do it. But we've already noticed that integrating is harder than doing the derivative. It's harder to recognize. And we have to like divide, and the ax plus b ones where we had to also divide by a. So it's a little bit complicated. And it's the end of the day. That's what happens. Some people have about 5 hours of proper behavior in them, and that runs out at about 2:30. So this integration by substitution is going to be like reversing the chain rule, but it's a little bit tricky to do. But if you're wondering, how do I know when to use this? You have to be able to recognize the chain rule and be able to see when, if you have a derivative, a chain rule happened, or at least something that kind of appears like the chain rule happened. And I'll explain more about what I mean by that in a bit. So this part, we are going to look at some of the examples we've done in the past. This is one of the ones that we did in the past that was super easy. It was really easy to see what the original function was, because here in yellow and then here in green is where the chain rule was. That yellow function was inside of another function. So when you did the derivative, you brought the 5 out in front first. So that is easy to see that that 5 got brought out in front first, and then the exponent became a 4, and then the chain rule would say you need to multiply by the derivative of the inside. Well, that green part is just the derivative of the inside part, which I'll highlight it in yellow. Of course, there could be a plus c. It could be a little c, could be a big c. I just wanted to mix it up a little bit. Well, originally I thought about making a big C. Okay. So if a chain rule is going to happen, we had a function inside of another function, and then there would be the derivative of that inside function happen afterwards. So that's the part that you have to start to be able to recognize. Inside of an integral, can you see one function that's inside of another function? Because that will still be there. And can you find the derivative of that inside function somewhere as well? So we are going to highlight the inside of the function that's inside of another function in yellow. So can you see that x squared minus 7 is inside of the power of 4? So it's the inside function. Does its derivative exist in this integral? What's the derivative of the yellow? 2x. And sure enough, that's there as well. The second one, can you see an inside function? Something inside of something else. The ln x is inside of that power 4. What's the derivative of ln x? 1 over x. And that appears as well. So the first part, getting us ready for integration by substitution, is being able to recognize when a chain rule has happened. The third one. Can you see that the 5 minus 2x to the 4 is inside of a square root? And the derivative of that? Well, the derivative of that would be negative 8x cubed. there's no negative 8x cubed anywhere. But there is an x cubed. So we're going to find out that we can still use integration by substitution even if the numbers or the coefficients, the numbers in front, don't work out nicely. Because this one on the left, and I've written it right here, it's the same as this. Here's that inside function. But on this one, I have it worked out perfectly, that I have the negative 8x cubed. But there's an additional negative 1 over 8 then that would be needed in front. So how are we going to deal with that? So with integration by substitution, we have to be able to see an inside function. We have to be able to recognize what its derivative would be, but not really have to worry about the numbers in front. Just like in this one, the derivative of an x to the 4 is an x cubed. I have an x cubed, so integration by substitution is going to work when we actually learn what that is. So all the way along in here, I want you to look at the next 5 before I highlight them and see if you can think, can I see the inside function? Is its derivative there? Can I see the inside function? Is its derivative there? See how you did. The inside function here is sine x. The derivative of sine x is cos x. This one's not as easy to see. The inside function is the 1 over that, because it would be like it's inside and it's something to the negative 1. The derivative of that, 3x squared minus 5. Inside function, the 3e to the x is inside of cos. What's its derivative? 3e to the x. The last one is interesting because there's no real inside function. I mean, there's a 2x is inside of sine and the 2x is inside of cos, but that's an ax plus b form, so that one doesn't really need to be done. But the derivative of sine is cos and the derivative of cos is sine, so in this case you could choose either one of those to be like inside a power of 1, but not really inside of it. No, it's not really inside of anything. So we'll have to see, how do we solve that one? Can we use substitution for that as well? And finally, the last one here, tan is inside of sine. The derivative of tan is secant squared. So integration by substitution is just that. You are going to substitute something in for something else. What do you substitute in? Well, you again look for your inside function. Here g of x is inside the function f. You look for the derivative g prime of x. And this time with my highlighter, I'm also going to highlight the dx part. We didn't do that on the last ones. I can go back and do that. We're going to find out that we're going to include the dx with the green part later on. What you're going to do is you're going to make u equal to g of x. And then if you took the derivative with respect to x of this, if u was equal to g of x, then du dx would be g prime of x. And if you rearrange this, which works really nice with integration by substitution, it can be proved in a rather complicated way, which we're not going to worry about, because du dx is the derivative. The dx by itself isn't a number, so technically you're not allowed to multiply both sides by it, but since it works really nice, we do. Okay? So it's a little bit of hand waving here to say that this g prime, we're replacing that with du. So our function, which originally was complicated, becomes simple. And when it's simple, it's going to be easy to integrate. And when it's easy to integrate, we're going to integrate it easily. And then substitute back at the end to get our answer. Okay? So this is a bunch of letters that mean nothing. Let's look at it with an actual equation and see what that means. So here we've already highlighted this one. We knew that this was the inside function. We recognized that we had the derivative there with 2x. How do we set this up? We always set it up by saying let u equal the inside function, x squared minus 7. Then the derivative, du dx, would be 2x. A little bit of hand waving, and we just say, well, then 2x dx is equal to du. Most of the time when you're doing this, you'll probably take the derivative and skip right from here to here right away. Once we've let u equal those things, we can now rewrite our integral with u's instead of x's. So what I'm going to write is, instead of x squared minus 7, I'm going to have u. So I'm going to have u to the power 4. And instead of the green 2x dx, I just have du. And if you had to integrate this, that's the easiest integral we can do. That's our power rule, right? What do? Add 1 to the exponent, divide by that number, plus c. Okay. Add 1 to the exponent, divide by 5, plus c. Easy peasy. And now that we've integrated, now we can go back and say, well, what did u actually equal? Well, we let u equal x squared minus 7. So the final answer for this one is x squared minus 7 to the power 5, all divided by 5, plus c. I don't know why there's that little, oh, there's a little 6 there. Because you have a 6 in your notes. Oh, it disappeared. There we go. Right there. Perfect. Not that the 4 was bad, but. So again, recognize we already highlighted that, oh, that's the wrong color highlighter. The ln x was the function inside. And the derivative of ln x is the x to the minus 1. We'll group that together with the dx. And that's what we want to substitute out. So we say let u equal ln x. Then du would equal 1 over x dx, which is the same as x to the minus 1 dx. And again, what started off looking really complicated with the substitution becomes really simple. So it's another one, add 1 to the exponent, divide, plus c. And so now we can substitute back. You know how, I have this urge right now. You know how this is equal to this, right? Should we be allowed to do that with logarithms? What do you think? Should we start a trend? No, it's like the whole thing to the power 7. Just like sine, you can put the 2 in between the sine and the x. Okay? This, should you be able to do that with logarithms? I mean, so that would mean if you had log base 3 of x to the power of 5, you could write it as log base 3 of x with 5 up there. Would that be too crazy? Oh, of x squared. Nice, yeah. You think we could create this? This video will change the world. Everybody from now on is going to be, because this happens so often in logarithms that you want to do it. I mean, okay, maybe not. Yeah, it's going to just like eat this one up. Okay. So again, what did we do? We found the inside function, substituted it out, got a really easy derivative, found, really easy integral, integrated. Yes? So the du, just like what happens to the dx, all that's there is telling you which variable to integrate with regards to. So originally, we needed to integrate this with regards to x. That's what the dx says. When you substitute the x away, you also want to substitute what variable you're integrating with. So now we're integrating with respect to u. So this du, just like that dx, is just telling you what variable you need to be considering. Because it could be you have multivariables. Now let's get to this one, because this was the first one when we highlighted things that didn't match up nicely. We had our inside function. Wrong color. We had our inside function 5 minus 2x to the 4. The derivative, though, is 8x cubed, negative 8x cubed, and we just have an x cubed. So we're wanting to get rid of the x cubed and the dx, but it doesn't match up perfectly. So how does it work? What happens? Well, we start off just like before, letting u equal the inside function, which was our 5 minus 2x to the 4. When we take the derivative of this, we get negative 8x cubed dx. We want to get rid of the green, which is an x cubed dx. Problem, we have an extra negative 8. How do we deal with that? How could I just get x cubed dx? I'd have to divide. I can either write it as divided by negative 8, or I can write a negative 1/8 in front. Now I have everything set up for substitution. What does this look like? This looks like the integral of, instead of the green, I have negative 1/8 du. That's on the top of my fraction. Instead of the yellow, I'm going to have u. Are you okay if I change that square root to a half right away? So I've substituted out. The nice thing is I just have numbers and powers right now, but I still need to work a little bit with this equation to get it into the place where I can easily integrate. So I am going to put that u to the top of my fraction by making it u to the negative half. I'm going to keep my number, negative 1/8, right at the front, because that's usually where the numbers are, and put my du at the end, because all that du is saying is what variable you need to integrate. And now this one is easy to integrate. Integreasy, yes. There we go, new word. We'll use that for the rest of the video. Okay, so what do? We add 1 to the exponent. That'll make a half. Divide by that half. That negative 1/8 would still be out in front, plus c. Dividing by a fraction, same as multiplying by a reciprocal. If I multiply this by 2/1, That fraction is going to simplify to -1/4. My u, when I substitute back, was 5 minus 2x to the 4 to the power of 1/2 plus c. Whew. This is a good example of one where even if you saw the chain rule to begin with, it might not have been easy to figure out that the final coefficient should be a 1/4. We are looking for our inside function. Highlight that in yellow, our derivative right there. So you always let u equal our inside function. Our derivative matches perfectly with what we highlighted in green. And so our integral changes to 5e to the u du. And that is integreasy.
Sounds like a really bad rap.
Yeah, maybe you could fill one out for me. Yeah. Thinks he's funny consistently. Is actually funny rarely. Okay. Before I go home and cry. Oh, good. I have to admit, of words that I have invented over my lifetime, integreasy is probably really low. You like integreasy? I don't know. It sounds greasy. Yeah. Okay, so there we go. There is our integral. This one, I think, is a little bit harder. I can go back to the last one. No problem. This one's hard to see an inside function because there's nothing like that's in brackets to the power 5. There's nothing inside of a sine or inside of a cos or in the exponent where an e is. So this function is harder to see what's inside. So in that case, just looking at it though, what this function does have is it's really easy to see that one is the derivative of the other one. So I can see that 3x squared is the derivative of x cubed minus 5x. So maybe that's going to give me a hint of what I need to do, because I don't really see an inside function so much here. So I start off by, well, if that's what it is, let's see what happens if we let u equal the yellow one, x cubed minus 5x. Then our derivative is 3x squared minus 5 dx. And we'll see what happens after I substitute this in. Again, I'm going to include my dx with the green there and see what I get. Well, that means that the green part just gets replaced with du. The yellow part gets replaced with u. And I could write this, because usually we have the du at the end all by itself, so then this would just be 1 over u. And even when we change it this, and this is supposed to be easy, this is the hardest one to recognize. But what is the integral of 1 over u? ln u. Ln u plus c. And now we can substitute back. So this one is ln of, what was our yellow? X cubed minus 5x plus c. And I think this is a great example of where substitution is important because initially, all you see is polynomials. There's nothing in that original function that should make you go, oh, a natural log. I see it. No, you don't see it whatsoever. But once you do the substitution, right, and you get to 1 over u, and you look at it for 5 minutes, all of a sudden you go, ah, it is the natural log. And then you can substitute back. And if you want to check, do the derivative of this. The derivative is going to be 1 over x cubed minus 5x. So that's where that makes sense that that x cubed minus 5x is on the bottom. And then multiplied, because of the chain rule, by a 3x squared minus 5. And that just got moved to the top of the fraction. But that's the same thing. I think we have time for one more. Yay. Back to an easier one. Easier to see the inside function. Inside function, 3e to the x. Easy to see the derivative. Substitute it in, and you've just got cos u du. And it's integreasy. So, well, is it positive or negative sign, though? That's the part that you have to think about. Positive sign. And so we have sine of 3e to the x plus c. Oh, I have put you guys through enough pain today.